Okay, so let's start back at the beginning again. Reiter moves. I want to begin today by cataloging some variations of knot theory based diagrammatically, some of which we might have a chance to refer to in more detail and some we might not, but it's worth pointing out some of these variations. So a recent variation that I think is very promising is due to Turayev, and he calls this variation knotoids. And a knotoid diagram, well, I won't write the words, but a knotoid diagram is a knot diagram, perhaps like this, where you have at the beginning you have one arc, but you could have more than one arc, and the arcs have endpoints, and the endpoints could be in any regions, possibly separated like they are here. Now you're used to drawing a certain kind of knotoid, which is usually called by some other name, like this. This is called a 1-1 tangle. But this guy over here is different and available to you once you have the idea. Now, what's the rule? The rule is Reiter moves are allowed, and something is forbidden, and what's forbidden is something like that. This is not allowed to slide an arc under the endpoint out, or over the endpoint out for that matter, so we might as well catalog the two kinds of forbidden operations. So as long as you now that's the way you would behave with a 1-1 tangle, right? When you're talking about tangles, you say, well, it's in a box and I'm only allowed to do the moves in the box. But here you don't have a good way to designate a box, but it's easy using knot diagrams to say, yes, but I will just allow Reiter moves, but I will not allow motion across the ends, and then this thing will stick around and you can try to classify them. So now that's a generalization of classical knot theory, and if you start to think about it, you realize, oh yes, some of the things that I know I could generalize here, and I won't go into all the generalizations, but let me show you one. Certainly you could write down a fundamental group, and you could do it combinatorially the way we did, or the quandle, because you see, if I label the arcs A, B, C, like this, and orient things if I wish, like that, why then I can write down a relation at that crossing using the same formula that I did yesterday. I just write C is equal to A inverse B A. And I write one relation for each crossing, and I write the generators, and I have a group with generators and relations, and you can check immediately, just like we did yesterday, that it's invariant under the Reiter moves. And the same proof works because there isn't any funny business with the endpoints. So you have a group for that. And it won't be the same as the group for the trefoil, not quite. So you have so it's clear you have lots of invariants for these knotoids, and there are different phenomena that occur with the knotoids that make them interesting. And also, you can think of the knotoid as a projection of something coming from 3 space, and let's think about that for a moment. That's why it's worth talking about in the context of applications. I'm just drawing some tracks here that will guide me in thinking about the knotoid, which is drawn in this plane in 3 space in relation to things that might go on above it. Now, it might have come from something above it, having been projected down this line. Endpoint lands here, other endpoint lands there. The entity that you see here goes around. It goes under. It goes around that post. It's seen to go under, and then I have it going back over. But what if, let me just push that up a little bit. What if up here in space this had gone way up here? This would still be projected down into the plane to the same entity that you're looking at, right? So you could have an open-ended arc up in space. And an open-ended arc up in space will look knotted from some points of view and will not look knotted from other points of view. Even if the open-ended arc was had a little tight knot in it, then you would likely say that it was knotted. But if you had something like this and you came upon it and looked at it from this point of view, you might say, well, it seems to be kind of knotted or sort of half knotted. What do I do with it? Well, what you can do is you can say, I will take an arbitrary arc embedded in three-dimensional space, and I will choose a plane of projection, and I will throw it down into that plane of projection, and then I will analyze the knotoid that you get. And this idea was come upon kind of independently of Turayev's definition of knotoid by Mark Dennis and some of his collaborators, and then more recently Dimos Gorandalis has been, did I pronounce your last name correctly? Where's Demos? There he is. Did I pronounce your last name correctly? Probably not quite. But anyway, Demos, if you saw his poster, has been doing exactly that with knotoids. The English people, Mark Dennis and his group, they had the idea of projecting an open-ended arc, and then they thought, oh, we'll use another variant of knot theory that we happen to know about called virtual knot theory, and we'll close it and make a virtual knot and examine it that way. I'll tell you about that in a moment. But another option is to just do this. And now think about this for a moment, and you will see that something is probably more or less intuitively clear. Which is that if I allow the knotoid to move by Reiter moves in this plane, then if I allow this to move upstairs up to isotopy, but I insist that these endpoints move along the tracks and never leave the tracks, so that I restrict the isotopies to isotopies that are good with respect to this projection, then I get exactly the same theory as the theory of knotoids that I just told you. The theory of knotoids as diagrams in the plane is the same as the theory of isotopies of open arcs in space on tracks, like that. So that means that if you have an open arc in space, you can't say that it's knotted or unknotted just bare. But if you look at all of these different projection and restricted isotopies, then you can say, well, over these regions of the two-sphere where I'm making projections, over these regions it's a non-trivial knotoid, and here it becomes a trivial knotoid, and here it changes its type, and so you can get a map, which is the sort of thing that Demos is doing, for example. You can get a map of how it looks from all the different points of view. And so this is a very sensible idea to generalize classical knot theory so that you can talk about open-ended entities. And open-ended entities, of course, occur all over in molecular situations, protein folding and DNA and so on. And so it makes a lot of sense to study knotoids, I say anyway, and I become a kind of an enthusiast of knotoids. And I've been writing some papers and doing some work with knotoids with Nestle Han Gugumsu, and you'll see some. I think these all have umlauts on them. You'll see our paper, one of our papers is on the archive, and there will be more. What we've been doing is making up invariants of these, and and we've been doing it by looking at classical invariants and looking at invariants of virtual knots, which I'll tell you about in a moment, and sometimes looking at very simple things. And I just wanted to mention something very simple here, and that is examine the Gauss code of this knotoid. Now, I think we didn't talk about Gauss codes yet, but let's talk. You label the vertices of the knot, the crossings of the knot, with some labels, and then you take a walk along it. In the case of the knotoid, you start from one end and you go until you get to the other end and say what the labels are. 1, 2, 1, 2. And then you can also say other things, like you could say over 1, under 2, over 1, over 1, under 2, under 1, over 2, and you could also keep track that this is a plus crossing, and this one is also a plus crossing. So you might keep track of all this information, and that's a complete Gauss code for it. Sometimes one draws a circular diagram with the numbers around the edges of the diagram, like this. And then you don't necessarily have to draw the numbers anymore, because you can draw some lines which tell you that it goes first 1, then 2, then 1, then 2, and you don't eliminate the labels. And then you can say over means that you have an arrow that goes out from that, and so it over 1, under 2, and then you can put the signs on the arrows if you wish, and this is called a Gauss diagram, and it's become a standard way to represent various things, and you could use it to represent a knotoid if you added a little extra information that said it starts here, perhaps, and doesn't come back to itself anymore. I just made that up on the fly. We haven't been using Gauss diagrams for knotoids much, but you could easily, and one tends to use them for knots. Now, the thing is that if you just look at the Gauss code all by itself, never mind the decorations of it, so I call this the bare Gauss code, and from now on when I refer to Gauss code today, I'll just be talking about the bare Gauss code. Then you'll notice that this has a parity consideration, that if you look from 1 to 1, you see an odd number of appearances of other symbols in between, and if you look from 2 to 2, you see an odd number of appearances of symbols in between. It has these both I would say that 1 and 2 both have odd parity. Take a look at a classical knot diagram, and look at its Gauss code, like this trefoil diagram, and you see that the code is 1, 2, 3, 1, 2, 3, and if you look in between any two of these, you'll see an even number of meetings. And in fact, it's clear that if you have an ordinary classical knot diagram and you take a trip from a crossing and go round until you come back to that crossing, which is what you're doing when you go from 1 to 1 here, that you will meet an even number of symbols as you go along. Now, in this case, it's quite clear why it's an even number of symbols, because this is some extra line in the diagram which crosses through this Jordan curve, and it has to go in and then it has to go out, and it's paired that way, and so you have an even number of intersections. Of course, this might be more complicated and have some self-intersections and wander around like this. But now what would it look like? You are walking from 1 and you get 2. You're walking along and you get 2, and then you get a bunch of other things, each of which occurs twice because you're going on the same curve, and you meet twice everything if you're going along the same curve, and then you meet 3, and so you ended up with 2 and 3, which were paired because of the Jordan curve theorem, and a lot of repetitions that just have to do with the fact that you're traveling on the same curve. So you see from this that if you have a classical knot diagram, then every crossing in the diagram will be even. But on the other hand, why was it odd when we worked with this? Well, for the very reason that there are endpoints. You walked around from here to there, and you counted how many things you encountered, but this 2 went in and it never left, and so it's possible for crossings to be odd. So parity can occur in natoids and will not occur in classical knots. It's a difference which can be exploited. And how shall we exploit it? Well, that's an invariant that is worth telling you about because it's so simple. So I'm going to define J of a natoid, and it's really the odd drive, and it's just some fact that I called it J a while back that I'm still calling it J, but this is the odd rive. So this is the sum over C, an odd crossing of the sign of C. All right. So over here in this, I obliterated. Let's draw it. Oh, here, this one will do. So what do we have here? We have that both of these crossings are odd, 1, 2, 1, 2, and this is positive. Oh, I'm sorry, I'm looking at the wrong one. Yeah, well, so what will happen here? None of these are odd. Let's go back to the one I had. I just wanted the signs. So both of these crossings are positive, and so the J for this is equal to plus 2. So what? Well, J is invariant under Reiter 1 and 2 and 3. Unlike Reith, which isn't invariant under 1. Well, why is that? Because there's no contribution from 1, because this crossing is always even. It's just empty, nothing's in between, and 0 is even. So 1 doesn't contribute for that reason when you're doing odd rive. And then you can check easily enough by doing a little parity checks that checking that it's invariant under 2 and 3. So there's an exercise for you. It's not a hard exercise. You can see that it will work. So so that means that we have a very simple invariant of natoids, namely the odd rive, and that tells us that this natoid is definitely non-trivial. There's no way to turn it into the unknotted natoid. Well, I guess we'll call it U. Yeah. No way to turn it into the unknotted natoid. And furthermore, what else do we know about it? So it's invariant. J of the mirror image is equal to minus J of the natoid, where the mirror image means you switch all the crossings. Because you switch all the crossings, you change all their signs. So you changed every sign that was in the formula, and so it changes sign. And J of a natoid is equal to 0 if K is equivalent to somebody like that. Well, somebody like that, where the endpoints are in the same region. If it's a knot-type natoid, an ordinary 1-1 tangle, then there wouldn't be any contributions. So we know, therefore, that this natoid cannot be manipulated so that these end up in the same region. They're one apart, one boundary arc apart from one another, and they will never get any closer than that, because then they'd be in the same region. And furthermore, we know that it's inequivalent to its mirror image. And that's quite a lot to get from such a simple invariant. We can't do that with ordinary classical knots, prove that a knot is non-trivial, prove that it's inequivalent to its mirror image with such a simple calculation. But here you can. So there's a little beginning with natoids. What else can we do with this generalization if we were thinking about what we've been doing in the last talk? Well, bracket K for natoids. You just repeat the definition. You expand in the usual way, the way you did the bracket before. And what will happen when you do that? What would happen if you were to expand this into a state? Just want to bring that down a little bit. let's consider what would happen if I try to compute the bracket of this. Now, I don't want to do the whole computation, but let's say we look at the A state. So I'll just draw it again and then smooth some crossings. So I smooth this crossing, getting an A there, and I smooth this crossing and I get an A there. And oh, you see, in this case, the state is nothing more than one of these little lines. So I'll put the A's on there and then we know what we've done. And what if I had taken another state? Maybe I smooth this in the B way and continue and smooth this one in the B way as well. All right, so now I get a loop outside and I get one of those long lines. So that's the general situation. I'll have some loops and I'll have some of these long segments. So you can make a choice about the long segment. I'll make the following choice, that the value of the long segment is equal to 1, and that the value of a loop next to anything is equal to the usual d times that thing, which is equal to minus a squared minus a to the minus 2 times the value of that thing. And the value of the loop itself will be equal to 1 as usual. And then we have some conventions that will do the bracket for us for natoids. And the invariance proof is exactly the same as the invariance proof that I finished with last time, because you're away from endpoints when you're dealing with the invariance. And you need the value of the loop as an isolated loop next to something to give you the right cancellation in the Reiter-Meister 2 move. So we have a bracket for natoids. And if you completed this calculation, you would find that indeed the bracket is telling you that this natoid is non-trivial. And everything goes through in that form. So what? So here's a conjecture. Two conjectures. For one, the old conjecture, conjecture number 1, is that the bracket polynomial for a classical knot detects the unknot. Now, what do I mean here? Since I didn't normalize the bracket yet, and I should, I would say that the normalized bracket is always, of course, is always 1 on the unknot, but the conjecture is that if the normalized bracket was equal to 1, then you have an unknot. On the other hand, if we go in this direction using just the bracket, you would get some power of a out of it. So if this evaluates to some power of a, then you should have an unknot. That's the old conjecture. But I see that I should take a little digression and talk about normalizing the bracket polynomial for a moment. You probably already know. So this is for classical or natoid. I define f sub k of a to be equal to minus a cubed to minus the rive of k times the bracket of k. And the rive is equal to the sum of the signs, not the odd rive, just the sum of all signs. The reason for this is because of a calculation that we didn't do at the end last time. What happens if you have a little curl? You're going to get a times the evaluation of this plus a inverse times the evaluation of that. And that's equal to a times minus a squared minus a to the minus 2 plus a inverse multiplied by the evaluation of the removed curl removed, and that's equal to minus a cubed minus a inverse plus a inverse, so this is equal to minus a cubed multiplied by the removal of the curl. And by the same token, if you were to put the curl the other way, switch the type of curl you got, then it will come out minus a to the minus 3, the inverse of that. Um, so then you see that this is going to compensate precisely for what this does, because what you're looking at here is local Rive contribution of plus 1. So if it multiplies by minus a cubed and you compensated by minus a cubed inverse, then it would be not behaving at all for that. It would be invariant under that. This is invariant under Reiter 2 and Reiter 3. This is invariant under Reiter 2 and Reiter 3. The product is therefore invariant under those two moves, and the product is, by its very definition, invariant under 1. And this, what I've said here, applies both to natoids and to knots, and we have this generalization. So then the conjecture, the old conjecture was that we could put it now this way, that fk of a equal to 1 implies k is equivalent to the unknot. That's the old conjecture, and the new conjecture is the same conjecture. Fk of a equals 1 implies that k is equivalent to the unknotoid. All right? I think they're equally hard. Conjecture number 1 is very far away from anyone solving it, as far as we know, but it's a bit surprising that it would get generalized, but as far as I can tell, by doing some examples, and you shouldn't believe me, of course, this seems to be a good conjecture too. If you're in the business of searching for counterexamples to this conjecture, it's probably a good idea to search for counterexamples to the larger conjecture over here. This conjecture includes this conjecture because natoids that are of knot type form like that are really the same as ordinary knots. You can just close them, you get the same results. So there's a couple of conjectures. Now, in relation to Kauffman's homology, we have Kauffman's homology for knots, and it is known that Kauffman's homology detects the unknot. And Kauffman's homology is extremely close formally to the Jones polynomial, to the bracket. If you form the correct Euler characteristic of Kauffman's homology, you get the F, as you know from Radmila's talks. So indeed, there is a Kauffman's homology on a paper that Neslihan and I would write soon, Kauffman's homology for natoids, and the construction is very similar, but we don't know certainly the theorem that Kauffman's homology for natoids detects the unknotted natoid. We don't know that. We might find that it is true if we could do a certain project, but the Kauffman's homology detects the unknot is a theorem at the present time due to Kronheimer and Moravka, and it uses some very interesting gauge theory and Floor homology of a certain kind, and they show that this knot Floor homology that they use has inside it certain chain complexes that are in fact the Kauffman's complex, and so they can compare it with this very powerful theory that they have, and so it's very far from combinatorics, and so it may or may not be the case that the knotoid Kauffman's homology complex can also be compared into that kind of gauge theory, but that's a project. I couldn't predict what will happen with that project. Anyway, I like this conjecture, and I've had some fun computing a few of these and feeling like it was a good conjecture. But I have to tell you that my track record with making conjectures is very bad, and so you shouldn't believe me. You should just take it as a way in which I'm telling you I think there's an interesting problem there, right? Okay, so that's whoops. Oh, yeah. All right. Let's take this up. Yeah. Right. Okay. Um, and then I wanted to tell you about another variation, and that's virtual knot theory. And so it's easy to say, but it requires some explanation. You add a new crossing. You keep the Reiter moves, and you add some new moves, and I'll draw them out. So these are just flat Reiter moves so far, right? Um, so that says that the virtual crossing not only does not know which way is up, but behaves as though it's just flat in the plane. And then, in fact, it even knows less than that in the sense that it's allowed to move across ordinary crossings. This is the important one, that we're allowing this. Okay, so you add this mixed Reiter move and these self-Reiter moves to the lexicon of moves that are allowed. I can summarize this by saying detour is allowed. Where detour means that you may have some consecutive sequence of virtual crossings, and maybe there's some other bit of diagram over here, and this will be equivalent to cutting this out and rerouting it over here like that. Oops. From here it got rerouted. And the rerouting, when it lays down on the diagram, is also like that. This is really a graph theorist's idea, or a graph theoretic idea. Suppose that at this level, suppose that you were talking about graphs which are not planar. For example, if you were a graph theorist, you might be interested in the famous gas, electricity, water problem graph, which has 3 points that are connected to 3 other points. And in order to draw it, I won't bother to figure out where the bipartiteness is in this, but there's the graph. This graph, the vertices in this graph are all these trivalent vertices here, and this is not planar. There is no way to embed this graph in the plane. One often draws, graph theorists will draw a crossing, which is flat, or they might even draw something like that, showing you how to embed the graph in 3 space. But I won't do that because that mixes up the metaphor. Or you could draw a little circle around the crossing just to remind you that it is part of the artifact of putting the graph into the plane. And then what rules would you take if you were a graph theorist and you had managed to put that graph in the plane this way? Then you would certainly say, well, this should be equivalent to, excuse me, I have to draw it all over again. This should be equivalent to rerouting this somewhere else. Maybe I would draw it like this. Not the most efficient drawing of that graph in the plane, but another one in any case. So that's one way of disturbing a given embedding into the a given immersion into the plane of a graph into another immersion of the plane. They should all be equivalent. And some of them are better than others in that they have smaller crossing numbers in the sense of the virtual crossings. And then there are other things that you can do to graphs to put them in the plane. You could change the order of the embedding cyclically around a vertex and so on, and that's the kind of consideration that happens in the graph theory. So we're saying the same thing here, that if you take a knot graph for a virtual knot like this one, then this should be equivalent to any rerouting that I care to make from here to here. So I could, for example, go crazy and draw something like this, just getting myself from here to there. And that's the same virtual knot. So I like to think of detour moves because it gives me the freedom to just do some large thing like that. But on the other hand, when you're working with virtual knot theory, sometimes you want to think of braids and other things, and so you factor what you're doing into those small moves, and it is true that you can factor any big detour move into a collection of small moves like that. Now, this sounds like just a very combinatorial generalization of the knot theory. But in fact, it has a geometrical interpretation that's quite nice. And the idea is this. Let's work from here and go into the geometrical interpretation. Suppose that I said, well, I want to think of this more geometrically, so I'm going to think of it as representing something that happened on a surface, and so I will cut out a little handle. I will cut out 2 holes from the plane, and I will add a handle like this. And I will run this up through the handle, and then I will put this underneath the handle like that. And I will say that this corresponds to that. Now, the first thing you will notice is that if you had done it the other way, the situations are homeomorphic. That is, you could have put a handle from here to here, and then get a picture like that. But if you put your fingers up into that handle from beneath the plane and give a pull, it will turn into the other one with the handle on the bottom of the plane instead of the top. So if we say we're making an abstract surface on which the knot diagram lives, then it doesn't matter whether I put the handle here or there. And so then you can envisage a specific virtual knot like this one as correspondent to a knot on a knot diagram on a surface, and a knot diagram on a surface. I'll draw another one in a moment, but there is a knot diagram on a torus if we think of this as happening on the 2-sphere. And you might start by looking at knot diagrams on a surface, like you might take a torus and doodle some knot diagrams for yourself on the surface, just like you do in the plane. And then you realize, oh yes, sure, there's a whole question of classifying knots on surfaces, by which I mean knot diagrams on surfaces, by which I mean actual embeddings of curves in thickened surfaces. But I prefer, in speaking, to just say knots in surfaces. But what I mean by knots in surfaces is knot diagrams in surfaces or actual knotting in the surface cross the unit interval, right? So then there's a whole question of what is the knot theory of those, and it's very complicated. And for a given genus, it's specifically complicated, having to do with the way things can wrap in that genus. We can simplify it a little bit by saying, well, if some of the genus is not being used, then I don't care, and I will regard this knot on the torus as the same as this knot on the genus 2 surface. So that means that I can consider the following theory: knots in thickened surfaces modulo handle stabilization. And by handle stabilization, I mean that you would be allowed to remove a handle if you could do it by a surgery that didn't involve the knot. So for example, in this case, I can draw this little curve, and I do surgery on that curve, which means that I cut along the curve and I add 2 discs, and now this part floats free and is gone, and the knotting that I'm talking about is now equivalent to this by handle stabilization. All right? So handle stabilization then allows me to shift the genus of the surface and throw away genus that I don't want, or add some genus if I like. And this theory is a perfectly good theory about knots in thickened surfaces that is worth studying by the usual philosophy of three-dimensional topology, and it may have some interest in applications where the knots find themselves being wound on surfaces. And I point out to you that it does happen. It happens with DNA winding around the histones. It happens with your own clothing, which is knotting, woven on surfaces. So, so we may be able to imagine applications here. Well, but I didn't say it, but it's true that this is equivalent to that. All right. This diagrammatic theory over here is equivalent to stabilized knots in thickened surfaces. And the way the way it goes is if you start with the diagram here, you can make it into a knot on a thickened surface by the handle addition that I just told you about, and that's the mapping going in one direction. And I won't go into how to do it in the other direction. Perhaps I won't. Yeah, I think I'd better not. But let me say a couple of words more about it so you get a picture. Let's just look at one thing. Suppose that I had a consecutive sequence of virtual crossings, maybe 3, yeah? And I tell you that you're allowed to do a detour move. Now, how would the detour move happen if I start thinking about handles? If I start thinking about handles the way I just told you, why then we'd have a handle here. Let's just do 2 of them. That's enough. And we'd have another handle here. All right. And we went above on that handle. And then we went above on this handle, and this line went underneath, and this line went underneath. Now, how am I going to pick that up somehow and move it somewhere else? It looks like it's rigidly bound to the way it's embedded in the surface, doesn't it? So there's a puzzle for you. Just a second. The surfaces are orientable. They don't have to be, but this is the best way to start this theory, is to just use orientable surfaces. Was that your question? Yeah. So I'm using orientable surfaces, and they're abstract surfaces. They aren't embedded in three-dimensional space. Although, of course, when I make the drawings and constructions, they tend to be visualized as embedded in three-dimensional space. But what I was saying really is that I wish it were like this. Because if it were like this, then I could start sliding the handle around on the surface and it would project down perhaps to some other part of the diagram. So that begins to look like my detour move, right? I wish it were like this. Well, in this case, you get your wish. Cut a little hole here. Cut a little hole here in the plane down there. Add a tube. That's allowed. That's a handle stabilization, right? It's allowed. It's equivalent. And now take your finger and push this down, and you end up over here. This is homeomorphic to 2 handles next to one another. You see? So that's an example of how handle stabilization is making the diagrammatic theory equivalent to the theory of the knots in the surfaces. And you do need the stabilization in order to make them equivalent. On the other hand, of course, you may be very interested, and I may be very interested in taking a specific genus surface and working out the knot theory for that surface exactly. And what does that have to do with this? So So far, I've told you a theorem, and I've only sort of roughly indicated why it works. The theorem is that knots in thickened surfaces modulo handle stabilization is the same as diagrammatic theory that I erased to Reiter moves and detour moves. But Berg proved a very nice theorem about this that completes the story in a certain sense. So Berg proved that if you represent a virtual knot diagram on a surface that is minimal genus, then the type, topological type in that surface is unique. So like you might have started with this virtual knot here and had it willy-nilly in a surface of genus 2, and you did some reduction, and you ended up with it embedded in a surface of genus 1, and then you perhaps proved that you couldn't ever embed it in anything of lower genus. Then this knot type in that surface is a unique knot type associated with the virtual knot diagram that you started with. You will never get more than one knot type in the minimal surface. So that means that actually the virtual knot theory is geometrically the study of those knots that are hugging in on their minimal surfaces. And if you knew the minimal surface, then it would just become unstabilized, and you would just try to study how it sits in that surface. Okay, so that's his theorem, and he uses a little surgery in order to prove that. Of course, it's not immediately easy to find the minimal genus surface. So that's virtual knot theory. And why do I mention virtual knot theory? Well, for a number of reasons, but in terms of knotoids, the reason is this, that if I have a knotoid, I keep wanting to draw a classical one. If I have a knotoid, then I can take its virtual closure by just connecting the two endpoints any way I like and making the crossings virtual. And I will get a virtual knot. And then you see easily enough that the virtual closure map on knotoids preserves invariants. Reiter moves over here, give over to Reiter moves over here. So the virtual closure of a knotoid is as a virtual type is an invariant of the knotoid, and that means that if I happen to have my favorite invariant of virtual knots, then it becomes an invariant of knotoids, and so one can exploit that and have a lot of interesting invariants of virtual knots. Now we're near about 10 minutes towards the end, so I'm going to stop talking about virtual knots, but that's a picture of this, I hope, and maybe I want to say one or two more things. Virtual knots have a well-articulated, maybe more than one, Kauffman homology associated with them, and so one can use that, and one can use that as the Kauffman homology of this if you want to, but you can do other things as well. There is something else I wanted to say. Oh yes, as you see, let's draw a picture of this. Take some knotoid. It doesn't always have to have its endpoint in an outer region, but I kind of chose that for my drawing purposes. So here's some knotoid, and never mind how the crossings were arranged. I'm going to virtually close it by having this enter the handle here. and come round, right? So you see that the kind of virtual closure that I get is always on a torus, right? Clear. So we end up with a subclass of virtual knots when we take their virtual closure. They're ones that are living on a torus, and mostly they're going to be, unless they're trivial, they really live on the torus. The thing I wanted to mention, which has to do with the somewhat edgy nature of the conjecture I've been telling you about, is that there exist virtual knots, non-trivial, with fk equal to 1, with Jones polynomial equal to 1. Now the generalization of the Jones polynomial for virtual knots of the bracket system is exactly the same as before. You just evaluate on a loop that happens to cross through itself the same way as if you had left it alone. Is that clear? So if I wanted to take the bracket polynomial of this guy, then I would expand it into states, and I might have something like this, you see, and that would be one of the state loops, and this will go to D. I just ignore the virtual crossings, and I get a bracket polynomial. In that sense of bracket polynomial, which is essentially the same sense that I'm using over here for virtual, for knotoids, there are non-trivial virtual knots with fk equal to 1, with bracket polynomial trivial, so that the conjectures do not work if you're over in full virtual knots. And I give you an example of that. Consider that. I claim that the Jones polynomial, or the bracket polynomial of that, is trivial. And the proof of this is easy, so we can do it. I'm taking the time to do this because it's fun, and I hope you'll enjoy it. So let's consider what happens with this little configuration here. And I'll do a bracket calculation, okay? So I expand this, A and B, and I get A expansion and A inverse. All right, but this is the same as pulling it apart because we ignore the virtual crossings, and the other one is the same as removing them because we ignore the virtual crossings. And this is exactly the same as, therefore, what happened when you expanded it without the virtual crossings on either side of it. So this, you could say this is a weakness of the bracket polynomial. It doesn't see this kind of twist, virtual twisting. And that tells us that this will have the same polynomial as what I will get if I do that to this diagram. And so I will do it to this diagram. So that means removing this one this way and this one this way. You have to respect the diagram like that. And what do I have here? So the bracket of this is equal to the bracket of this, and this is, as you look at it carefully, there's a little loop going entirely over, pulls up. So after you normalize it, that tells you that fk is equal to 1. So, of course, you might say, well, maybe it's trivial anyway, but it's not. And I'm a little bit out of time, so I won't do the exercise that proves that it's non-trivial. Oh, yes, I will. Remember, we did 3 coloring yesterday, right? So 3 coloring will do it. Let's 3 color this. The situation works the same way, only you take the same color, you take the colors straight through the virtual crossings without doing anything to them. So A, A all the way over here. Here's a B. This will be C. C propagating all the way over to here. C times A is B, and B times C is A. It's three colored, right? And if it's three colored, then by the argument that we made last time, it can't get rid of the colors by the Reiter moves. And so this is a non-trivial knotoid, a non-trivial virtual knot, excuse me. And it has Jones polynomial equal to 1. There are infinitely many of them, and it's just happening that you won't hit any of them when you do this kind of virtual closure. And you won't hit any of them that are constructed this way, and that requires a little work, but you won't. So, so the conjecture is, to someone who's used to virtual knot theory, a little more edgy than it might have been otherwise, in that you're coming nearer to a place where the Jones polynomial does fail, but not so near that that this isn't a reasonable conjecture. So I spent a lot of time on these variants today, and I want to take 5 minutes to do something about statistical mechanics, because I told you I would, and then we'll continue with that and some other remarks about covariant homology in the last lecture. But let me allow me to make these remarks about statistical mechanics. So now I'm leaving knot theory for a moment, and I'm telling you about a certain kind of function that occurs in physics called the partition function. So G represents a physical system, and you sum over sigma, which is a state of G, e to the minus 1 over kt, energy of the state. And this is temperature. And this constant is called Boltzmann's constant. And in actual physical applications, it has a value. And there are good physical reasons for exponentiating the energy, which I won't go into. You'll notice that if the energy is high, then this exponential is small. This is called the partition function. And e to the minus 1 over kt, energy of the state, is supposed to be proportional to p of the state, where I mean by that probability of the state, okay? All right, prob. So the probability of being in that particular state of this physical system is e to the minus 1 over kt, energy of the state. You can start to think about, well, what if I raise the temperature? What happens to the probability? And so on. If that's the case, then this is the denominator for finding the actual probability of the state, right? This tells you that in this way of speaking, the actual probability of the state is going to be equal to e to the minus 1 over kt, energy of that state, divided by the partition function. That's so that the sum of the probabilities will be equal to 1. And so you see, for doing statistical mechanics, this is obviously an important function to have around. And you want to know, how does it behave with respect to temperature? How does it behave with respect to the geometry of the system? And if you knew it, you could differentiate logarithmically differentiate with respect to t and bring the energy down, so you can find the average energy from the partition function by differentiating it, and many other things. So this is a kind of quantity that's ubiquitous in statistical physics, and was studied by people for simplified models. And the reason why there is a great interest in very simple models of statistical physics comes from the success in solving things about the limit of the Ising model. And kind of problem that's involved there is that the G in this simplified physical system is a graph, and maybe it's just a rectangular n by n lattice graph like this, where the energy is the sigma at this site I will be equal to plus or minus 1 for Ising. So you could think of a magnetic vector, magnetic spin up or down, for example, at every point in the lattice. And you may impose some conditions like periodic boundary conditions and ask for the partition function if you can assign an energy to the system in terms of the local behaviors of the spins that are nearby one another. So you can write down in the Ising model, one would write down an energy functional that recognizes whether these spins are the same or different and add up over the whole thing to obtain the energy. I'm going to stop now rather than go on and define things more particularly. But the next model, but the point is that in the mid 1940s, Onsager was able to understand the behavior of the limit as n goes to infinity of this n by n g over here, the partition function of that gn, and showed that the system has a phase transition. Which means that there's a critical temperature, and it behaves one way on one side of the of the critical temperature, and another way on the other side, just like liquid to gas. And this happens on the basis of extremely simple graphical definition of the system, which can be generalized to POTS, and I'll tell you POTS because that's the one I'm going to use. In POTS, the sigma I would belong to a larger set, and we'll just make them all positive, a set of choices up through Q, and then if these are the same, if sigma I equals sigma j, then add 1 to the energy. All right, so you just count how many times there are coincidences, and that's the energy, just the number of coincidences. And then that's the partition function. And it's on an arbitrary graph instead of just a rectangular graph. That seemed the natural generalization. This is very hard, figuring out this limit. And people were excited, and so they started examining other geometries. POTS is a nice generalization, but no one has completely solved the POTS model in the sense of for an arbitrary Q, understanding what these limits look like, even for the rectangular lattice. And the Ising model hasn't been solved if you had generalized this in the obvious way to 3 dimensions. But one of the things that happened in the early 1970s is that Temperley and Lieb figured out, I'll stop writing, Temperley and Lieb figured out a formula for the POTS partition function, and they showed that it was a graph theory polynomial, the dichromatic polynomial, if you take the parameters right. I'll show you that at the beginning of next time. So then this turns out to be right on top of the formalism of the bracket. So what we'll see at the beginning of next time is that the POTS partition function is a graph theory polynomial, and I'll show you how it is. And then I'll show you how that graph theory polynomial can be written in terms of the 3-variable bracket that I defined. And so you have this interrelationship, direct interrelationship between statistical mechanics and the topology in that form. And the relationship is really very interesting. Temperley and Lieb figured out an algebra that described their model called the Temperley-Lieb algebra, and a diagrammatic version of that comes out naturally if you're working with the bracket, which can then be used and is used by people in statistical mechanics. And there are probably lots more interrelationships between statistical mechanics and the knot theory, including Covanoff homology and things like that. We can speculate, and I'll stop talking now and continue for the last time.